Molt bona tarda i molt benvinguts al que jo diria aquesta sessió científica que crea expectació i també de molts resultats de la investigació científica en el camp de la física. Jo vull excusar especialment l'assistència del doctor Jaume Carot, que li hagués agradat molt poder assistir i estar aquí amb la doctora Cintes i amb el doctor Bona, però circumstàncies personals no hi pot ser. I en tot cas el que sí hem comentat la importància d'aquest acte d'avui hora baixa aquí a la seu de la nostra universitat. Sens dubte pensam que el segle XX va ser el segle de les grans revolucions científiques i entre elles podríem destacar tant la mecànica quàntica com la teoria de la relativitat, també l'indeterminisme i, en el meu cas, com a matemàtic, també diria els teoremes de la indecidibilitat de Gödel. Totes aquestes revolucions han tingut profundes implicacions en la manera de pensar i d'imaginar la realitat i també importants aplicacions pràctiques que han millorat la nostra societat i, en particular, la salut i el nostre benestar. I amb això es demostra una vegada més que allò que s'anomena recerca bàsica és imprescindible, tot i que els seus beneficis materials sovint es veuen de manera molt diferida en el temps. Al segle XXI encara no sabem què serà globalment, però tot apunta que, com a mínim, serà el segle de les grans confirmacions i els grans descobriments. Només, si ens referim a la física o a l'entorn de la física, podríem recordar que el juliol de 2012 es trobava al CERN el bosó de Higgs que havia estat predit amb un model estàndard l'any 1964. Enguany es commemora el centenari de la primera publicació de la predicció d'Albert Einstein sobre l'existència de les ones gravitacionals. Coincidint amb l'efemèride i la finalització del primer període de funcionament dels detectors LIGO, els investigadors de l'MIT, també de Caltech i la col·laboració científica del mateix LIGO, reunits per la National Science Foundation, es reuniran avui hora baixa per donar a conèixer els esforços que s'estan fent per observar i mesurar les ones gravitacionals a la recerca científica. Com a rector voldria remarcar la importància del Grup de Relativitat i Gravitació de la Universitat en aquesta experimentació i en particular perquè és l'únic grup de recerca d'Espanya que forma part de la col·laboració científica d'aquest gran projecte LIGO, en la qual és un projecte que hi participen més de 1.000 científics de 15 països i la seva participació ha estat molt important, vull dir, la seva participació com a grup de recerca de l'UIB ha estat molt important dins d'aquesta col·laboració. El Grup de Relativitat i Gravitació té una llarga història dins del Departament de Física de la UIB. Des dels seus orígens amb el doctor Lluís Mas a principis dels anys 80, després també en la incorporació l'any 1983 del doctor Carles Bona, al qui ràpidament li passaré la paraula, que és l'impulsor de l'actual institut IAC3 i també actualment és el director del Departament de Física, i en aquest mateix any la incorporació del doctor Jaume Carot com a estudiant de doctorat. Més tard s'hi van incorporar el doctor Joan Estela i com a estudiant de doctorat del doctor Carot s'hi va incorporar la doctora Alicia Cintes, que també ha tingut aquest protagonisme tan important dintre del grup de recerca vinculat en el LIGO. S'han incorporat més recentment d'altres investigadors com el doctor Carlos Palenzuela i actualment aquest grup de recerca compta amb molts doctorants de diferents països i també de postdocs i molts d'ells relacionats amb aquest gran projecte LIGO. Sense més preàmbuls, més que felicitar coralment el doctor Carles Bon i a la doctora Alicia Cintes i també el doctor Mas com a impulsor i com a primer persona que en aquest departament va dur el tema de la relativitat, doncs agrair tot aquest esforç que heu fet, mantenir aquesta posició que té la universitat dintre el món de la investigació, que sens dubte sou persones cabdals, i en particular a la doctora Alicia Cintes com una de les investigadores més citades de la nostra universitat. Per tant, moltes gràcies, enhorabona, i que avui sigui un gran dia i una gran tarda. Doctor Bona, quan vulgui.
Moltes gràcies, senyor rector. És un plaer per jo, a la meva condició de director del Departament de Física, però també de cap del Grup de Relativitat, presentar avui a la doctora Alicia Sintes. Tal com ha comentat el rector, avui doctora Sintes va començar fent la tesi doctoral amb en Jaume Carot sobre aspectes matemàtics de la teoria de relativitat. Quan va acabar la tesi va venir al meu despatx i em va dir que volia variar un poc, volia canviar un poc de tema. Jo li vaig explicar el que jo personalment feia i la gent que feia feina amb mi, la meva línia, que era simulacions d'ordenador per veure com se movien els forats negres, i li vaig dir, bueno, si algun dia se troben ones de gravitació, voldríem saber quina és la firma d'un forat negre en aquestes ones de gravitació, i per tant això vol dir que primer ho has d'haver estudiat a l'ordenador. I em va dir, això no és prou diferent del que jo feia, per això encara tu fas, Carles, encara té masses matemàtiques, jo vull una cosa més diferent. I llavors l'opció que entre ella va trobar i nosaltres també la vàrem donar suport és posar-se en contacte amb el professor Bernard Chus de la Universitat de Cardiff. S'estava iniciant llavors la part experimental, més experimental, dels projectes de detecció d'ones de gravitació. De manera que la doctora Sintes va obrir dintre del nostre grup una línia més experimental d'anàlisi de dades en relació específicament amb les ones de gravitació. I per això avui estem aquí. Com vostès que són periodistes hauran sospitat, no és un informe rutinari de la feina que hem anat fent, sinó que hi ha cosa grossa. I sense més preàmbuls passo a la doctora Sintes.
Moltes gràcies, senyor rector. Moltes gràcies, senyor Carles Bona, com a cap de departament i cap del grup nostre. És un plaer. Gràcies, companys, per estar aquí, alumnes que també em veig, i també medis de comunicació. Moltes gràcies per haver vingut aquí. I abans de connectar exactament, esperem, sent puntuals, amb Washington, a seguir la roda de premsa, l'important, us faré aquí una introducció sobre les ones gravitacionals i que fem el grup sense dir-vos res. Tindreu que esperar després a saber de què va això, per què us han cridat. Molt bé, com ho acaben de dir, va ser l'any 1915 en què l'Albert Einstein va presentar la seva obra mestra. Allà on presentava aquesta teoria de la relativitat general. I un any després, ell mateix va publicar el següent article allà on parlava ja d'aquestes ones gravitacionals. Curiosament, va ser el mateix Einstein que va pensar que les ones gravitacionals eren massa febles per poder ser detectades i ell mateix no creia en forats negres, que és una altra de les coses que prediu la seva teoria. Llavors, què són aquestes ones gravitacionals? D'acord amb aquesta teoria d'Einstein, la gravetat no és una força qualsevol, sinó que està relacionada amb la curvatura de l'espai-temps. D'alguna manera, l'espai-temps li diu a la matèria com s'ha de moure i l'espai-temps li diu a la matèria com s'ha de moure i la matèria li diu a l'espai-temps com s'ha de curvar. És una cosa curiós. Què passa llavors? Quan la matèria se mou, d'alguna manera la curvatura ha de seguir a la matèria. Però això no ho pot fer instantment, perquè la informació com a molt viatja a la velocitat de la llum. Llavors, amb això, se produeixen pertorbacions. I aquestes pertorbacions, ondulacions en el teixit de l'espai-temps, se propaguen per tot arreu a la velocitat de la llum i són aquestes ones gravitacionals. Els fenòmens més exòtics i més violents de l'univers són aquells que produeixen les ones gravitacionals de major intensitat. Aquests, per exemple, són col·lisions de forats negres, expulsions de supernova, esclatxos de rajos gamma i, com no, l'event més violent que ha ocorregut mai, el propi Big Bang. És a dir, que amb aquestes ones gravitacionals podem veure i podem obtenir una informació de l'univers quan aquest univers encara no tenia ni tan sols un segon de vida. És a dir, que anem enrere molt més temps que podem observar amb la llum, en radiació electromagnètica. És a dir, el repte, ara, avui en dia, amb les ones gravitacionals, primer de tot és poder-les detectar, però també poder extreure tota la informació que contenen. Aquestes ones gravitacionals ens ajudaran a explorar grans qüestions de la física, tant de la física fonamental, de l'astrofísica i de la cosmologia. Alguns dels exemples és com se van formar els forats negres, si la relativitat general és la descripció correcta de la gravetat, o fins a quin punt, i com se comporta la matèria sota condicions extremes, entre moltes preguntes més, i com no, també descobrir coses noves. I què fan aquestes ones gravitacionals? Aquestes ones gravitacionals van viatjant i mentre se van propagant distorsionen l'espai-temps. I què vol dir això de distorsionar? Doncs simplement que per una banda ens comprimeixen i per l'altra me l'estiriguissen mentre van passant, de forma successiva. Ara, aquest estiriguissament i compressió és extremadament petit. És a dir, en un cas realista d'una ona gran, de gran amplitud, estem xerrant que ens la distorsiona amb una part, com a molt, amb una part entre 10 a la 22, que traduït vol dir que si jo considero la distància entre Sol i Saturn, la distorsió màxima, la més grossa, que això farà, serà del tamany de l'àtom d'hidrogen. I això, per això Einstein deia que no es detectarà mai. I això és el que volem detectar a la Terra. A la Terra, evidentment, aquestes distàncies no les tenim tan grans. Tenim detectors de, com a molt, el més gran, que és l'LIGO, té longituds de 4 quilòmetres. I, per tant, aquest és un instrument de gran precisió que ha de ser capaç de veure desplaçaments, mesurar-los, d'un tamany inferior a una mil·lèsima part d'espordor. Llavors, evidentment, això és un gran repte tecnològic, es desenvolupar aquests instruments, però existeixen. I es pot aconseguir mesurar aquestes distàncies tan petites amb interferometria làser, que no entraré en detalls. Simplement que es tracta amb llum llàser, se separen els feixos i després s'intenta reconstruir. Si passa un feix, la manera en què es mouen els dos braços és diferent. I per tant, intentant mesurar quant de diferent se m'allarguen i se m'acurcen els braços del detector. Això no és ciència-ficció, sinó que aquests detectors existeixen. Fins al 2010 hi havia tota una xarxa mundial de detectors que estaven operant i prenent dades. En particular, l'LIGO estava prenent dades del 2002 fins al 2010 en 6 períodes d'observació. Però, des d'aquell any, només GEO, el petit de 600 metres que està a Alemanya, a prop de Hannover, és el que està seguit operant, perquè tots els altres s'han desmantelat al seu interior per posar grans actualitzacions per fer-los molt més potents. Llavors, d'aquests instruments més potents tenim Advanced LIGO, pròximament Advanced Virgo, en un futur al voltant del 2018 Kagra al Japó, i en un futur un poc més llunyà, un dels LIGOs, el tercer LIGO, s'anarà a la Índia, però que aquest encara no està ni començat a construcció. Llavors, què és LIGO? LIGO consta de 2 observatoris, un a Hanford, a l'estat de Washington, a el desert, i l'altre a Livingston, a l'estat de Louisiana, entre alligators. Llavors, aquests són 2 interferòmetres, cada un d'ells, els seus braços són de 4 quilòmetres de longitud, que estan financiats per la National Science Foundation i que són concebuts, construïts i operats per Caltech i MIT. Però la ciència relacionada amb aquest observatori la fa la col·laboració científica LIGO, LIGO Scientific Collaboration, com heu sentit, hi ha més de 1.000 persones involucrades, més de 90 institucions, a 15 països, entre aquests països, Espanya. I aquí teniu tots els logos de les col·laboracions en tots els noms de les institucions. La UIP, la Universitat de les Illes Balears, des del 2002 és membre oficial de la LIGO Scientific Collaboration, i no només de la LIGO Scientific Collaboration, sinó també del detector petit que està a Alemanya, de GEO 600. Aquest és la foto actual dels membres oficials de la col·laboració LIGO a la UIB, allà on hi ha també el doctor Sasha Husa i jo mateixa, que som els 2 IPs que portem a la recerca de la part de LIGO, 2 estudiants de doctorat, 2 estudiants de màster, un postdoc, i 2 estudiants de grau que estan fent el treball de fi de grau amb nosaltres. Tant Sasha com jo formem part del Consell de LIGO i jo formo part de LIGO des de l'any 97, que és quan me'n vaig anar a Alemanya a començar aquesta nova aventura. Ara què ens dedicam a la UIP? El treball del grup de la UIP es centra en la cerca d'ones gravitacionals provinent tant de forats negres com d'estels de neutrons i, a la vegada, tot el modelatge computacional que se necessita per poder identificar aquestes fonts. Se desenvolupen aquí models realistes d'aquestes fonts, generant catàlegs molt precisos de perfils d'aquestes ones gravitacionals basades en aquesta teoria d'Einstein i cream models molt sofisticats analítics de la fusió d'aquests col·lapses de forats negres que poden ser emprats per fer l'anàlisi de dades. Per fer això implica que, primer de tot, i abans de poder construir aquestes aproximacions analítiques, s'han de fer moltes simulacions numèriques i aquestes se fan a grans superordenadors, entre ells Espanya empram el Mare Nostrum i també empram infraestructura europea. D'aquestes simulacions podeu anar al nostre nou canal de YouTube, que això és el treball de fi de grau de Rafael Jaume, allà on, a partir de les nostres dades, ha fet una feinada, i no sé quan se n'ha sortit, de reconstruir tota una sèrie de pel·lícules i a les 4:30, quan els secrets ja no seran més secrets i tothom els podrà desvelar, encara apareixeran molt més vídeos que els que vulguin de recursos es podran baixar. També hem contribuït molt de software a el que és la llibreria de software de la col·laboració i també al projecte de computació distribuïda Einstein at Home. No entraré en detalls, fes un Google i cerqueu el que és. La UIB també ha liderat diferents cerques de senyals contínues procedents d'estels de neutró a les 6 períodes d'observació del LIGO inicial, que va tenir lloc entre el 2002 i el 2010. Ara, com heu escoltat, al setembre de l'any passat va entrar en funcionament LIGO avançat, que no encara està a disseny final. Llavors, aquí teniu una comparació de quina era la sensibilitat de LIGO el 2010, quan havia estat operant. I aquí teniu els dos detectors LIGO, la sensibilitat ara obtinguda, i aquesta és la sensibilitat de disseny que s'espera assolir el 2020. I aquí ja ha millorat un factor 3, que és molt, perquè no esperaven que en la primera vegada que això entraria en operació arribàssim a aquesta sensibilitat. I aquest factor 3 implica que en volum són capaços ara d'escanejar un volum 27 vegades més gran del que es podia escanejar a final del 2010. I això possibilita que hi pugui haver deteccions. Els detectors han estat operant fins al, no ho veig, però el 12 de gener d'enguany i encara s'estan analitzant dades d'aquest Science Run. A més, un dels nostres estudiants de doctorat, Miquel Oliver, aquí present, es va passar 3 mesos a l'Observatori de Hanford, a l'hermós desert, allà dalt, fent shifts a les sales de control. Hi va estar des de tot el mes de setembre, octubre i novembre, i n'estic segur que aquest període que va fer allà no l'oblidarà mai. Aquí us deix aquesta pàgina, allà on podeu agafar notes, aquí el grg.uib.es.ligo, és una pàgina especial expressa que hem fet per l'ocasió, allà on trobareu tota la informació que aquest grup està fent, com hi participam, qui som, què fem cada un de nosaltres. També trobareu més recursos i a partir de les 4:30 trobareu extenses notes de premsa de la UIP, també trobareu el resum científic i algunes curiositats més de 4 de nosaltres, de què és el que recordam, de com vam viure alguns dies d'un cert mes, que encara no puc dir. I si teniu més interès sobre què són les ones gravitacionals, aquesta altra pàgina pública, que la tindrem que actualitzar la setmana que ve un poquet, tindreu recursos i informació sobre, en plan divulgatiu, sobre què són aquestes ones gravitacionals. Trobareu també vídeos, trobareu jocs traduïts o adaptats pel grup i més tal. més coses. Bueno, vaig molt bé de temps i això és el màxim que us puc dir abans de connectar amb Hanford, excepte que ens podeu seguir al Twitter, ens podeu seguir al Facebook i que d'aquí una estona ara és YouTube.
Good morning. Welcome to our distinguished visitors, members of the press, NSF staff, and National Science Board members represented by Dr. Maria Zuber of MIT. Scientists from the LIGO, Virgo, and GEO scientific collaborations, members of the Caltech and MIT communities, and all our guests. I specifically want to recognize representatives from the Max Planck Society, the UK Science and Technology Facilities Council, and the Australian Research Council, whose generous contributions have also helped bring us to today. I'm Dr. France Cordova, the director of the National Science Foundation. Without a doubt, the reason so many of us are here today is because we believe in the potential of the Laser Interferometer Gravitational Wave Observatory. Opening a new observational window would allow us to see our universe and some of the most violent phenomena within it in an entirely new way. Since the mid-1970s, the National Science Foundation has been funding the science that ultimately led to LIGO's construction. And in 1992, when then NSF Director Walter Massey and the National Science Board approved LIGO's initial funding, it was the largest investment NSF had ever made. It was a big risk, but the National Science Foundation is the agency that takes these kinds of risks. We support fundamental science and engineering at a point along the road to discovery where that path is anything but clear. NSF funds trailblazers. It's why the U.S. continues to be a global leader in advancing knowledge. So, without further delay, because I too am eager to hear the latest updates from LIGO's lead scientists, let's kick things off with a video and then go to Dave Reitze, who is LIGO's executive director.
Gravitational waves were predicted by Einstein about 100 years ago, and they are dynamical perturbations in the fabric of space-time, ripples in space-time, if you will.
The gravitational wave stretches space in one direction and compresses space in the other direction.
Nobody really believed that you could ever detect them because the size of the effect is so small.
I came to the conclusion that, yeah, if you made this long enough.
Nobody had ever made something like this before, so there was a lot of technological challenges that needed to be overcome.
That's what scientific discovery is really all about. You don't choose the simple things to do.
We have done something which is brand new.
The field has busted wide open.
It's monumental. It's like Galileo using the telescope for the first time.
I looked at it and I thought, my God, this looks like it's it.
Ladies and gentlemen, we have detected gravitational waves. We did it. I am so pleased to be able to tell you that. So these gravitational waves were produced by two colliding black holes. came together, merged to form a single black hole about 1.3 billion years ago. They were detected by LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is the most precise measuring device ever built. Let me start with what we saw. So on September 14th, 2015, the two LIGO observatories in Hanford, Washington and Livingston, Louisiana recorded a signal nearly at the same time, nearly simultaneously, and the signal had a very specific characteristic. The characteristic of, as time went forward, the frequency went up. And what was amazing about this signal is that it's exactly what you would expect, what Einstein's theory of general relativity would predict for two big massive objects like black holes inspiraling and merging together. Now, it took us months of careful checking, rechecking, analysis, looking at every piece of data to make sure that what we saw was not something that wasn't a gravitational wave, but in fact it was a gravitational wave. And we've convinced ourselves that's the case, and we're here to announce that today. But I do want to say something else. This is not just about the detection of gravitational waves. That's the story today. But what's really exciting is what comes next. Right? It's 400 years ago, Galileo turned a telescope to the sky and opened the era of modern observational astronomy. I think we're doing something equally important here today. I think we're opening a window on the universe, the window of gravitational wave astronomy. So I'm going to show you two videos that are going to sort of tell you what we discovered. So the first video is the two black holes. So what you're looking at on the screen here are two black holes. Each of them are about 30 solar mass, have about 30 times the mass of the sun. All right, and you're looking, the black holes are the black things in the middle, and you're looking at the stars behind them. By the way, this is not a Hollywood production that I'm going to show you. It is actually a real computer simulation solving Einstein's equations for these merging black holes. So this is really what it would look like if you were in a spaceship close up. And I will also point out that the movie I'm showing is vastly slowed down relative to what happened here. So let me start it. All right, you can see that as the black holes spin around each other, all right, the stars behind them are warped, and that's because the strong gravitational fields bend the light that comes around. But what I want you to pay attention to in this video is the fact that as they orbit, the black holes are getting closer and closer to one another. The orbit is speeding up, and eventually they're going to merge. The event horizons are going to join, boom. They produce one big black hole, which relaxes, and you see a little bit of vibration there, and it becomes two smaller black holes die, one bigger black hole is born. Now, what's really amazing about this is the first time that this kind of a system has ever been seen, a binary black hole merger, and it's proof that binary black holes exist in the universe. So I want to put this in perspective for you because I think it's very important, all right, to give a sense of what really happened here. So each of these black holes are about 150 kilometers in diameter, a little bit bigger than that. Take something that's 150 kilometers in diameter, so that's about a little bit bigger, maybe a lot bigger than the metropolitan Washington, D.C. area. Pack 30 times the mass of the sun in that. Accelerate it to about half the speed of light. Now take another thing, 30 times the mass of the sun, accelerate at half the speed of light, and collide them together. That's what we saw here. It's mind-boggling. All right, now, let me talk about the gravitational waves. You didn't see any gravitational waves there. What you saw was actually black holes. Now let me look at this from the gravitational wave perspective. So you're going to see, again, a computer simulation. This is a real simulation using Einstein's equations. You see the two black holes. And the green that you see are the gravitational waves that are produced as the black holes orbit around one another. Their orbit decays and they merge together. All right. So they're spinning around. You see they're getting closer and closer together. As they get closer and closer together, more gravitational waves, they merge, and there's this burst of gravitational waves that travels for 1.3 billion years. It passes through everything. It goes right through matter, right through stars, and it eventually gets to the Earth. All right, and when it gets to the Earth, the gravitational wave passes, and what it's going to do is stretch and compress space as these waves pass, and you'll see that the Earth is jiggling like jello. I don't want people to be scared here. The Earth doesn't really do this. This effect is greatly, greatly exaggerated, but it gives you the effect. And then we zoom in, and how we detect these are using the interferometer that's in LIGO. And Ray Weiss is going to tell you more about the interferometer. I just want to say one thing, that the effect that we're trying to measure from these violent, these big black holes colliding each other at half the speed of light, all right, is so tiny that it takes something like LIGO to measure it. We are trying to measure things basically at 1/1000th the diameter of a proton. That's the size of the signal that you see on Earth from those events that take place 1.3 billion years away. All right. Let me put that in perspective, because I think those kinds of numbers are hard to get your head around. All right. If we were trying to measure the distance between the sun and the nearest star, which is about 3¼ light years away, LIGO is capable of measuring that, if it could do that, to a level of about the width of a human hair. So the width of a human hair over 3¼ light years. That's remarkable precision. Right? Now what LIGO does is it actually takes these vibrations in space-time, these ripples in space-time, and it records them on a photodetector, and you can actually hear them. So what LIGO has done, it's the first time the universe has spoken to us through gravitational waves. And this is remarkable. Up till now we've been deaf to gravitational waves, but today we're able to hear them. That's just amazing to me. I think this is big, again, because what's going to come now is we're going to be able to hear more of these things. And no doubt we'll hear things that we expected to hear, like binary black holes or perhaps binary neutron stars colliding. But we will also hear things that we never expected. And as we open a new window of astronomy, we may see things that we never saw before. So let me conclude by thanking the National Science Foundation. For 40 years, since the NSF started funding Caltech and MIT to do pilot experiments for LIGO, and then in 1992, the NSF went ahead and funded the LIGO project, right? And they took a big risk, all right? This was bold. The science was solid, but we didn't know how many events we would see. The technology was nowhere near developed. This was truly, I think, a scientific moonshot. I really believe that. And we did it. We landed on the moon. So I really want to thank Dr. Cordova and NSF, and also U.S. Congress, taxpayers who supported this research, because it's really, really gotten to the point now where it's going to take off. So I'm going to conclude my remarks, and I'm going to introduce my esteemed colleague, Gabby Gonzalez. Gabby is a professor of Louisiana State University. She's also the spokesperson for the LIGO Scientific Collaboration, and she's going to tell you more about this event and about the team that discovered it, and about the observatory. So I turn it over to Gabi.
Thank you. It's an honor to be here to tell you about this fantastic discovery. This discovery has taken a long time. This has been a long journey, but it also has been the work of many people. There's only a few of us here, but there are now more than 1,000 people working on this, and there have been hundreds of people developing the technology, doing the analysis, and building these detectors. We are very proud of this work taking a village, a worldwide village. That was the LIGO Scientific Collaboration working together with the Virgo collaboration in Europe. And we have been analyzing data from 2 detectors in Hanford, Washington, and Livingston, Louisiana. LIGO built 2 detectors because we are measuring these tiny distortions of space-time here on Earth that you can only believe they're real if you see them both at the same time on places that are far apart. That's the only way to be sure that these are not local disturbances and they are coming from astrophysical sources. These detectors are L-shaped. This is the LIGO Livingston detector. They are 4 kilometers long on each side. That's a Hanford detector. And we have lasers that go back and forth between mirrors
to measure the distance between those mirrors. And gravitational waves would distort the space-time and would be measured as distortions in that distance of 4 kilometers. Again, it takes a lot of people to do this, and you can see a lot of people, young people doing this, as well as people who have been working on this for decades. So this is it. This is what we saw. September 14 last year, we saw this signal in Livingston, Louisiana. That is a measure, that's a waveform that we saw. The units are strain, that's a distortion of space-time, and you can see a peak value. The largest value of this waveform was a part in 10 to the 21. For 4 kilometers, that's a tiny, tiny fraction of a proton diameter. That's incredibly tiny. But this signal is seen, you can see it even by eye, above the ever-present rumbling noise that we have in the detector. But we know it's real because 7 milliseconds later, we saw the same thing in the Hanford detector. This is it. That's how we know we have gravitational waves. But we know a lot more than that. You can see that these signals have oscillations that grow in frequency and amplitude and then settle down. And that's exactly the prediction that we know from solving Einstein's equations on computers for the coalescence of two black holes, merging into a larger black hole and settling down. And the coincidence is remarkable. You can see here overlaid the template that we used, or the numerical relativity simulation that was done for the coalescence of these black holes. That's how we know not only that we detected gravitational waves, but these waves were produced by the coalescence of black holes. So these are the fantastic news we're telling you about. Now, from these waveforms, you can tell a lot more. You can tell from the frequency the masses of the initial black holes. They had 29 and 36 solar masses. From the fitting to the numerical relativity waveform, we can tell that when they merged, they formed a larger black hole, but not with the sum of the two masses, with only 62 solar masses. And that's because there were 3 solar masses emitted in energy in gravitational waves. That's a huge amount of energy. And we can tell all of that from this tiny fraction of a second in the waveform. We can even tell more than that. From the amplitude of the waveform, you can tell how far away this system was. It was more than 1 billion light years away. This merger happened 1.3 billion years ago, when multicellular life here on Earth was just beginning to spread. And the signal took 1 billion years to come to Earth and produce this tiny distortion in our detectors that we are very proud to measure. Now, you can read a lot more details about these things in a paper that has just appeared online, peer-reviewed in Physical Review Letters. We are also publishing a lot more details in other papers that will be made public. Now, we can also put these waveforms, we can make a color plot time frequency diagram, and you can see the color denoting the amplitude, so it gets brighter as time goes on, and then dimmer when the black hole rings down. You can also see that the frequency is increasing, and the frequencies of these waveforms are in the human hearing range. We can hear gravitational waves. We can hear the universe. That's one of the beautiful things about this. We are not only going to be seeing the universe, we are going to be listening to it. Now, I wanted to play the gravitational wave for you to hear, but it's so short that it's just a thump. So what we have done is taken the real signal and shifted a bit in frequency, but it's still the real signal. Did you hear the chirp? There's a rumbling noise, and then there's a chirp. Let me do that again. answer we've been looking for. This is the signal we have measured. We can even tell more. Because we have two detectors, it's like having two ears, we can localize the signal. Not very well with only 2 ears, but we can tell it came from the southern sky in the rough direction of the Magellanic Cloud, and we could have a broad area, a broad uncertainty area for the region. Of course, the source is a very point-like source. I mean, the merger happened in a small region, but we cannot tell exactly where it happened because we only had 2 detectors. But this will get better. We will have a network of gravitational wave detectors. GEO 600 has been working for decades as a technology demonstrator, but Virgo is going to come with a sensitivity closer to the LIGO detectors later this year. So we will have 3 years to localize the signals. And later on, we hope to include in the network the Kagra detector in Japan, and hopefully one in LIGO, India, very soon. So this is just the beginning. We discovered gravitational waves from the merger of black holes. It's been a very long road, but this is just the beginning. This is the first of many to come. Now that we have detectors able to detect these systems, now that we know that binary black holes are out there, we'll begin listening to the universe. Thank you. We hear now from Ray Wise, one of the founders of LIGO, who will tell us about the history and the technology in these amazing detectors. Thank you.
Well, I'm going to tell you a little about history and then some about the instrument. And I want to first remind you of Einstein's 1915 big discovery, which was celebrated just recently, was really the formulation of these field equations, which were a completely different way to look at gravity. I mean, most of us were taught Newton. We talked about forces in gravity. Einstein didn't have that conception. He had the conception that actually space gets distorted. And you can see this in this picture of a membrane that is sitting under the sun, which is that yellow object, and then you can see a little dimple that's made by the Earth. And what that distortion in space and time is the thing that also tells those objects how they're supposed to move. So it's a completely different and a radical different idea about how gravity operates. And then in 1916, he applied these field equations to the idea of gravitational waves. There had to be something that communicated information, and it couldn't go faster than the velocity of light. That was already known. So what he then found is that there were waves in this theory that moved and propagated the velocity of light, and what they were strains in space. And I'll show you a strain in space, that's so you can visualize it. Here is this thing that, I don't know, I hope you can see. It's not the easiest thing. I'm going to make believe the gravitational wave that you're being demonstrated is coming at you. And I'll be the agency that moves the universe here. And you'll notice an interesting thing about it. If you look at any pair of points on this thing, what is a strain? A strain is the difference in distance that 2 points have as a function of time divided by their initial separation. And you'll notice that in the middle of this thing, it's small. That's strain. The strain is the same all over this, but the amount of motion is small in the middle. It's quite large at the edges. And that's one of the reasons now you have some image why we had to build LIGO to be so big. You have to overcome a lot of other things that are going on. So we wanted to make sure that we made it long enough so you could see this. Now, even with this wonderful, enormous source that you've just heard about, and you know the numbers, the Einstein, first of all, could never have conceived of that. But even, let's just look at it. What it is that in the early days of, let's say, 1916, Einstein probably looked very hard at doing things himself on TBI. He was a practical physicist. He was a patent clerk. And what he probably did is he saw that these waves were generated by accelerating mass, and he probably put on the backs of envelopes, and we're looking for those envelopes. People don't have them, but they had to exist. Some calculations. Could you move a mass? That's big enough. Could you measure it with the existing devices that existed in 1916? And you couldn't. Einstein was very despondent about that. He also then looked at, astronomical systems like binary stars, and the ones he knew about in those days had long periods, and they just would never change aspect. Nothing would change about them as they were radiating gravitational waves. It was just too small. And so what's happened since then is two things have happened. One is that astronomers have found compact objects like black holes and neutron stars, which change the whole aspect of how fast things can accelerate. And then the other thing that really has changed is the technology. And that is an enormous step in the last 100 years. So with that, you're still now having these things, and I'll describe how we do this in a minute. Let me get you a little perspective. You've already had some, but I want a different perspective on what 10 to the minus 21 means. Okay? 10 to the minus 21 strain, everybody's saying, is 1,000th the size of a nucleus. So let's get to a little visceral feeling about that. I mean, the strain is 10 to the minus 21. If you now multiply that by 4 kilometers, you wind up with 10 to the minus 18. 10 to the minus 18 meters if you use. Okay. Now, what is that? And most people don't know the 10 to the minuses, so they like to have it as, it's a decimal point and 17 zeros and then a 1. Okay, that's so, if you have to think of it as a fraction. And now let's look what that is. Start with a meter and divide it by a million 3 times over. First time you divide it, you get a micron. So 10 to the minus 6. That's sort of the size of a cell, or maybe the 1,000th of your hair. Well, you've got much more to go. Then you divide by another million. And now you're at 10 to the minus 12. That's about 1/100th the size of an atom. And you're still not there. And now you divide again by another million, and you get to this number that we have to measure. And that's the 1,000th the size of a nucleus. So how do we do it? Well, we do it by timing light. That's how we do it. And I'll show you this in this. Here's a Michelson interferometer, which is the device that does the measurement. And what you'll see this round cylinder there, that's a laser. It's a make-believe laser. Then there's a beam splitter, which is that thing, which is a thin little thing in the middle. Then there are 2 mirrors, which have those black aspects, one to the left, one to the right. And then a make-believe detector, which is that rectangular thing. And now let me turn this animation on, and what we do is we fire light from the laser into the system. Now this is the electric field in the light. The color is the intensity of the light. So you'll see where the color tells you where the light is. But the electric field is indexed by the different colors of the field. And you'll notice the way this was set up is that right now there is no light at the photodetector. That's the trap you've set for the gravitational wave. And now people begin to wiggle in the animation, the end mirrors. And you'll notice light appears, disappears at the photodetector. That tiny motion and that fact, that light, the amount of light that goes to the photodetector is proportional to that strain in the gravitational wave. That's the method of the detection. Okay, now you're not done yet. You've got a device that measures tiny motions or tiny differences in time. But you're not done because you see those mirrors are sitting on the Earth, and the Earth is very noisy. It jiggles everything. And you want to make sure that the thing that jiggles the mirrors is only the gravitational wave. So we use all sorts of tricks. And I'll show you one of the tricks. Here's one of the tricks. What we do is we suspend the mirrors from a pendulum. Here's a sort of demonstration pendulum. And here's the mirror. And my hand will be the ground motion. And you notice if I move it very slowly or at low frequencies, the pendulum follows me. It follows the ground motion completely. Now let me wiggle it fast. And you'll notice the pendulum stands still while I'm wiggling. That's the basis of the idea. Now that's done with a tremendous elegance and, with cunning in this picture. This is what's actually in the apparatus. You see it on the screen now. And that is now 4 of these things in series, okay? And by the way, the principle I just showed you is very much like the principle in a car. It makes you comfortable in a Cadillac and sort of bumpy in a truck, yeah? Okay. Now, the thing is, you're not done yet. because there are other forces you have to worry about. And they are thermal noise, there's all sorts of noise, even quantum noise in this system. And all of that technology which has been developed, had it been available to Einstein in 2016, I would have bet that he would have invented LIGO. I mean, he was smart enough and he knew enough physics. He wasn't just a theorist, okay? All right, now I'd like to introduce to you Kip Thorne, who is both a theorist and really an experimenter. And he was a visionary in this field because he thought about this many years, thought about all the sources, thought about what the theory really meant. And I want to give you a nice example from Kip's life. He wrote a book, a popular book that many of us have read. It's called Black Holes and Time Warps. And it says the undertitle is Einstein's Outrageous Legacy. And in that book, he tries to introduce the public to all those wild things that go on in the theory. And he has a group of people on a spaceship commanded by a woman who are going to visit all different kinds of black holes. The first place they go to is a stationary black hole. And that is like the one in our own galaxy. Then they go to a spinning black hole, and they look at that for a while. But then, very carefully, they approach a pair of black holes weighing 24 solar masses that are going around each other. And they merge into a single black hole. And then the universe gives a little burp when that is over. That's all in that book written, well, a chapter of that book was written in 1983. Okay? And we actually have seen it. So, Kip.
Don't forget your toys, baby. Ray is a modest man, but you should know that he was the primary inventor of the interferometers that detected these gravitational waves. And major additional contributions in terms of ideas came from Ronald Drever, who is the third founder of LIGO along with Ray and me. Unfortunately, Ron is too ill to be able to be with us today, but his family and he send their greetings. LIGO has been a half-century quest. It arose in part in the 1960s from pioneering work by Joseph Weber at the University of Maryland. And it arose from interferometer R&D in the 1970s and 80s at Caltech, MIT, in Scotland, and in Germany. In the late 1990s, Caltech and MIT built facilities for LIGO with funding from the National Science Foundation. And then in the late 1990s, LIGO was expanded to include scientists from many universities around the world and many nations, as Gabby Gonzalez described to you. In the 2000s, the initial interferometers were built and operated in LIGO as precursors to the advanced interferometers that we were telling you about today. The advanced interferometers were installed in between 2010 and 2015. They carried out their first gravitational wave search beginning last autumn with spectacular results almost immediately. Now, until now, we have only seen warped space-time. We as scientists have only seen warped space-time when it is very calm. As though we had only seen the surface of the ocean on a very calm day when it's quite glassy. We had never seen the ocean in a storm, roiled in a storm with crashing waves. All of that changed on September 14. The colliding black holes that produce these gravitational waves created a violent storm in the fabric of space and time. A storm in which time speeded up, then slowed down, speeded up again. A storm in which the shape of space was bent in this way and that way. We have been able to deduce the full details of the storm by comparing the gravitational waveforms that LIGO saw with the waveforms that are predicted by supercomputer simulations. And so here I'm going to show you a video that describes at the very bottom, it's not very bright, but at the very bottom is the gravitational waveform that was seen, cleaned of all of its noise. and it agrees beautifully with the gravitational waveform predicted by the simulations. And by seeing which simulation agrees in gravitational waveform, we can then go in and look at the computer simulation and deduce what I show you for the storm in the middle of the screen. And time is shown in the upper left of the screen, the flow of time. Now, the shape of space I show to you by imagining that we are living in a higher dimensional universe looking in on our universe. I take away one of the 3 dimensions from our universe, so it looks like a surface, a 2-dimensional surface. And the flow of time, and then I should say that the funnels that you see in there represent the warping of space around the black hole. The flow of time is represented by the colors. In the green region near the center, time is flowing at its normal rate. In the yellow regions, it's slowed by 20 to 30%, and in the red regions, it's tremendously slowed. The silver arrows describe the motion of space. It's dragged into motion by the spins and the gravity and the movement, the orbital movement of the black holes, and then the motion of space causes the orbit to precess, as you saw. I'm pausing the movie now to watch the onset of the collision. You're going to see in slow motion the growth of the warping. I'm going to pause it, stop it here for a moment, and you can see the extreme warping, and then we see it oscillate and settle down finally into a single black hole. A new black hole has been born. Far away, in purple and blue, we see the gravitational waves propagating toward Earth, carrying the news of the collision. Now, the storm was brief, 20 milliseconds, very brief, but very powerful. The total power output in the gravitational waves during the brief collision was 50 times greater than all of the power put out by all of the stars in the universe put together. It's unbelievable, 50 times the power of all the stars in the universe put together. Because it was so brief, the total energy was not that big. It was only what you would get by taking 3 suns, annihilating them, and putting them into gravitational waves. Well, that's kind of a lot. And so, colliding black holes are not the only source of gravitational waves that LIGO will see. We will see gravitational waves from spinning neutron stars, stars the size of Washington, D.C., made of pure nuclear matter, weighing more than the sun, with little mountains on their surfaces that as the stars spin, those mountains generate continuous gravitational waves, long-lasting gravitational waves. We'll see gravitational waves from black holes tearing neutron stars apart, gravitational waves from neutron stars colliding. We are searching for gravitational waves from the central core engines of supernova explosions. And amazingly, we're searching for gravitational waves and have some hope of finding them from cosmic strings, giant strings that reach across the universe, that are thought to have been created by the inflationary expansion of the fundamental strings that are the building blocks of all matter, that expansion, inflation at the beginning of the universe. Now, LIGO has opened a new window onto the universe, a gravitational wave window, but all of our previous windows through which astronomers have looked are electromagnetic. The astronomers look, for example, with optical telescopes through the optical window, radio telescopes through the radio window, X-ray telescopes on board satellites through the X-ray window. And each time a new window has been opened up, there have been big surprises. The universe seen through optical telescopes was very serene. As seen through radio telescopes and X-ray telescopes, it's tremendously violent. Gravitational waves are so radically different from electromagnetic waves that I think we can be rather sure that we will see big surprises, perhaps even bigger surprises through the gravitational wave windows than we have seen through the new radio and optical radio and X-ray windows. LIGO is just the beginning with gravitational wave astronomy. Over the next decade or two, we will have 4 gravitational wave windows opened onto the universe. There's LIGO looking at gravitational waves with oscillation periods of milliseconds. There will be a window with gravitational waves that oscillate with periods of minutes to hours. There will be a window with gravitational waves that oscillate with periods of years to decades, and a window with billion-year-long oscillations. It is really remarkable that LIGO is such a fantastic beginning. Now I'd like to turn this back to Dr. Franz Cordova, the director of NSF. But I'd like to do so in thanking Dr. Cordova and her predecessors for a fabulous 40-year partnership between NSF and the LIGO collaboration. We began with a high-risk dream with very high potential payoff, and we are here today with a great triumph, a whole new way to observe the universe. Dr. Cordova.
Wow. Einstein would be beaming, wouldn't he? This is obviously a very, very special moment. It's a very special moment for me personally to be able to hug a faculty mentor when I was a graduate student at Caltech, and hearing Kip and Virginia Trimble, the spouse of Joseph Weber, inspire students with stories of black holes, which seemed imaginary at the time. And look where we've come now. It's just amazing. So today, you and the hundreds of collaborators who have made this discovery possible mark this day as truly historic. I commend each of you, as well as all the NSF program directors who have stood by you steadfastly for about 40 years. Let's give a big hand to our NSF program directors.
El que vau d'escoltar, que les ones gravitacionals han estat exactament detectades 100 anys després de la predicció d'Einstein, i que això ens està obrint l'aigua una nova finestra cap a l'univers en l'observació d'ones gravitacionals procedents de forats negres. La història l'heu sentida, va ser el 14 de setembre, seré breu. Aquí acabaven de tornar de la reunió de LIGO a Budapest, vam veure allà prou caos, veníem aquí, organitzaven els encontres relativistes espanyols, el divendres defensava Àlex la seva tesi doctoral i dilluns, dia 14, era el primer dia de classe a la UIB. Allà on semblava zona zero, Mateu Orfila, dintre i de fora. Ordenadors que tenien distribuïts per tot arreu i a les 11:50 hora espanyola arribava a Terra aquesta senyal. En menys de 3 minuts, un còdic anomenat Coherent Words Burst, que no l'hem escrit nosaltres, però el que Sasha Husa, professor d'aquesta universitat, és un dels revisors, només va tardar 3 minuts, o menys de 3 minuts, en l'Online System, en registrar això a la nostra d'això i enviava un mail automàtic a 3 persones. A aquesta hora a Espanya encara dormen als Estats Units, excepte que un dels 3 autors d'aquest còdic està al Max Planck a Alemanya, es diu Marco Drago, i en menys d'una hora va escriure més o menys que dir què punyetes està passant, perquè hi ha un detall tècnic aquí, que és que el RAN no havia començat. Estàvem en el que se deia període de proves, estàvem fent proves, estàvem en Engineering RAN 8 abans de començar el període d'observació. I d'això de mails d'aquests, són els típics mails, aquí agárrate como puedas, i acaba, no està marcat com una injecció en hardware, són les brometes que ens fem a nosaltres mateixos. I entenem, després d'algunes investigacions, que realment no hi ha injeccions de hardware. Pot algú confirmar que no hi ha injeccions de hardware? Molt bé, aquí també hi havia idea de caos. Les propostes per demanar temps de càlcul a les Mare Nostrum, o a les centres de la red de supercomputació espanyola, era a l'endemà. Hi havia que acabar d'escriure les propostes. Aquí hi havia molt de nerviosisme, que tothom estava escrivint. Inclús el futur postdoc, que tenia un gripàs, que se'n tenia que anar, i encara no el tenien contractat, també escrivia proposta. No va tardar una hora que aquí començaven a entrar e-mails, com un tsunami, aquest tsunami d'e-mails encara ha aturat. És a dir, no m'escrivieu un e-mail, per favor, no m'escrivieu un e-mail. El dia calmat són 200, i jo no els reps tots. Estava clar, quan en Sasha es va relaxar un poc, ens van començar a mirar gràfics, i teníem a nostre agente infiltrado, Hanford, que estaven volent que xiqués ja, i que mos digués què punyetes passava a la sala de control. Llavors, com veus, s'han observat les ones gravitacionals procedents, és a dir, hem observat ones gravitacionals, hem observat una parella de forats negres i hem observat el col·lapse d'aquests forats negres. I això està publicat des de fa, espero, 30 minuts, a Physical Review Letters. La senyal que us he mostrat era molt lletja. Si jo blanqueig la senyal, un altre tema tècnic, la senyal comença a ser més maca. És a dir, hem vist la fusió de dos forats negres de 36 més 29, produint això. El quocient senyal-soroll era de 24, que es converteix en això de 5,1 sigmes, és a dir, que han superat la barrera dels 5 sigmes. És a dir, el primer event que hem vist ha estat un event clar. Un pic d'energia alliberada de 3 masses solars amb una fracció de segon, que és una quantitat d'energia brutal, com heu escoltat. Això no ha estat només un article que s'ha publicat, hi ha un altre citat a Astrophysical Journal Letters, i hi ha totes aquestes coses d'aquí de papers que també ara apareixeran online, o quasi tots. No sé si han estat tots acabats ahir vespre. I al costat d'aquí, veus uns números en vermells, i és a cada un d'aquests papers quantes vegades pipen papers de la UIB, en alguns casos inclús fins a 10. I aquí teniu la senyal a un gràfic temps-freqüència i veus com la senyal ha augmentat. Freqüència amb un interval extremadament petit de temps, i aquest és el millor filtre que va en la senyal. Aquestes coses els podeu sentir, és com un ocell, i a mi jo amb els braquis no ho sé dir. Fa uup! Això és el soroll que van escoltar aquests detectors, com heu sentit. I això són els articles que s'han citat a aquests papers. Entre ells, n'hi ha 3 que vull destacar, allà on Xisco també és coautor, i l'antic postdoc, i en David que també. I els models descrits en aquests articles han contribuït des de la UIB a poder identificar aquesta font. És a dir, tota la línia de recerca de Sasha Huss amb els seus forats negres, les simulacions i els models han impactat. I un dels resultats claus que s'ha inclòs ara aquest article, l'article principal, és la potència radiada per la font, 300 masses solars per segon, que és més que qualsevol aconteixement mai vist. Ara direu, bueno, ja ho heu detectat, heu acabat, no hi ha res més a fer. Evidentment, queda molt a fer. Queda encara analitzar cuidadosament les dades de la segona meitat a la cerca d'aquestes ones de col·lapses gravitacionals, de forats negres o estels de neutrons, però també altres recerques. I per alguns de nosaltres, com Miquel i jo, ara tenim una feinada, perquè quan ells acaben d'analitzar, entrem nosaltres a cercar estels de neutrons, que són encara molt més febles, i necessitem integrar les senyals durant els 4 mesos del període d'integració. I els detectors tornaran a anar online al setembre, juntament amb Virgo, i per tant hi ha que preparar-se. Aquí teniu fotos de nosaltres, està això online, l'hem perdut. Treballant, tots els que són, alguns dels grups, i alguns acabats de marxar, que havien defensat tesis enguany o un antic postdoc a altres centres de recerca. I jo vull acabar la meva presentació per agrair, primer de tot, a tots els membres del grup aquí, estudiants inclòs que hi han col·laborat, per el treball que hem fet des del 14 de setembre, perquè d'hores de dormir n'han dormides poques. De classe no n'he preparat ni una. Està clar, d'enguany. I també per ser el comportament exemplar, perquè fins que no va saltar el País i l'Avantguàrdia, el Departament de Físiques no en tenia ni punyetera idea del que punyetes fèiem a les quartos de bany del segon pis. I de les telecons i les nerviades, i que si no funcionen, les llicències i no sé què. Evidentment, també vull donar les gràcies a la Universitat de les Illes Balears per tot el suport que ens ha donat tot aquest temps, pagar clústers, llicència de matemàtica i altres coses, i això és extensiu a tots els serveis administratius, comunicació, premsa i de més aquí, que també hem fet una feinada i m'han tingut que aguantar a mi tots aquests dies, i des del centre de càlcul, centre de tecnologia i informació, que ens han ajudat de forma incondicional en tots els requeriments que li han anat demanant. Formant part, com hem dit al principi, de l'Institut d'Aplicacions Computacionals de Codi Comunitari, del que és fundador Carles Bona, i també som part de l'Institut d'Estudis Especials de Catalunya. I hem tingut el recolzament financer, tant del Ministeri d'Economia i Competitivitat, Govern de Balear i Comunitat Europea. Gràcies.